Imagine you're decoding an alien language with only a list of sorted words. Can you reconstruct the whole alphabet? Alien Dictionary is a Pattern Mastery 100 Super Challenge. Regularly asked at Google, Meta, and Amazon to test your grasp of graph theory, topological sorting, and string manipulation. Over 40% of candidates either miss edge cases or get tangled in cycle detection. Master this, and you'll shine on advanced ordering problems. Let's break down Alien Dictionary using the basic method, giving you a foolproof plan for any graph-based string ordering challenge. Given a list of words sorted according to an unknown alphabet, return a string representing the alphabet's order. If no valid order exists, cycle, return. List of words, all lowercase letters, possibly with overlaps and missing letters, a string of characters, the alien alphabet order, or if invalid. Suppose you're designing a search tool for a new language, or analyzing a secret code with custom rules. An interviewer might ask, how would you deduce task dependencies from log order, or infer a dictionary structure from partial data? What's tricky? You need to infer order constraints between letters by comparing adjacent words. Must detect cycles. If two letters are required to come before each other, there's no valid order. Not all letters may be present in the input, and some may be missing from certain orderings. Build a graph. Each unique letter is a node. For every pair of adjacent words, find the first position where they differ. That's a precedence constraint. Edge. Topological sort. Apply Kahn's algorithm, BFS, or DFS to produce a valid order. Use an indegree map to track how many incoming edges each node has. Add nodes with 0 in degree to the result. Decrease in degree as edges are used. Cycle detection. If at the end, you haven't used all letters, result is shorter than unique letters, there's a cycle. Let's clarify. If a word is a prefix of another but comes later, it's invalid. For example, ABC, AB. All letters in words must appear in the output. Edge cases. Empty word list. Return. Words with same prefix. Skip until the first difference. Cycle in constraints. Return. Initialize a graph, adjacency list, and in degree dictionary for all unique letters. Compare each pair of adjacent words. For each character, find the first mismatch. Add an edge from char 1 to char 2. Char 1 comes before char 2. If one word is a prefix of the other and is longer, return. Topological sort. Add all nodes with 0 in degree to a queue, while queue isn't empty. Pop from queue, append to result. Decrease in degree for neighbors. If in degree becomes 0, add to queue. If result length equals the number of unique letters, return as a string. Otherwise, return, cycle or invalid input. Let's walk through this solution. The main goal here is simple. Deduce the correct order of characters in an alien language from a sorted word list. If we mishandle prefix conflicts or cycles in ordering, the inferred alphabet will be invalid. If we carefully build a graph of ordering rules and run topological sort, everything works smoothly. Approach. Graph plus topological sort, OV plus E. Time complexity, OV plus E. Starts the method that returns the alien alphabet order as a string. Creates a map to track how many prerequisites each character has. Creates an adjacency list, for each character, which characters come after it. Loops over each word in the list. Loops over each character in the current word. Ensures every character appears in the indegree map with default 0. Ensures every character has an adjacency set initialized. Ends inner character loop. Compares each word with the next one to derive ordering rules. Stores the current word and the next word. Finds the minimum length to safely compare characters. Checks the invalid case where a longer word comes before its prefix, for example, ABC before AB. If that invalid prefix situation occurs, return an empty string, no valid order. Walks through both words character by character. Reads the characters at position J in each word. Finds the first differing characters between the two words. Avoids adding duplicate edges for the same ordering rule. Adds a directed edge. C1 must come before C2. Increases the indegree of C2 because it has one more prerequisite. Ends the duplication check block. Stops comparing this pair of words once the first differing pair is processed. Ends the if C1 equals C2 block. Ends the inner comparison loop over J. Ends the outer loop over pairs of words. Creates a queue for BFS topological sorting. Iterates through all characters we know about. In queues characters with no prerequisites as starting points, will build the final alien character order, performs BFS until there are no more nodes with indegree 0, retrieves a character with current indegree 0, appends it to the ordering result, visits all neighbors that come after this character, reduces the indegree of each neighbor since C is now placed. If a neighbor now has no remaining prerequisites, add it to the queue. Ends neighbor loop. Ends BFS loop. If we placed all characters, return the order. Otherwise, a cycle exists, so return empty string. Ends the alien order method. Ends the solution class. And that's how the alien dictionary algorithm works. Efficient, simple, and elegant. Now let's verify that this solution behaves correctly on the provided test case. This list is already sorted according to the alien dictionary. It matters because by comparing adjacent words, we can infer ordering constraints like W less than E, E less than R, and R less than T, which together define part of the alien alphabet. Short reasoning of how the algorithm processes the input and what it checks for. The code first registers all characters, W, R, T, F, E. Then it compares each pair of adjacent words. WRT versus WRF gives T less than F. WRF versus gives W less than E. Versus ET gives R less than T. ET versus RFTT gives E less than R. These edges build a graph. WERTF. Topological sorting from nodes with indegree 0 produces the order WERT. This output makes sense because it respects all constraints. W comes before E, E before R before T, and T before F, matching the structure implied by the word list. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's walk through this solution. The goal is simple. Recover a valid alien alphabet order from the sorted list of words. By building a directed graph and running DFS with cycle detection, we can produce a valid order, or detect that no order exists. Approach: DFS plus topological sort, OV plus E. Time complexity, OV plus E. Defines the solution class used by LeetCode. Flag that tracks whether the graph remains valid, no cycles. Starts the main method that returns the alien alphabet order. Adjacency list, for each character, which characters must come after it. Collects all unique characters appearing in the input. Loops through each word to gather characters. Adds each character to the global set. Iterates over adjacent word pairs to derive ordering rules. Detects the invalid case where a longer word appears before its prefix, for example, ABC before AB. Finds the first differing character and records the ordering rule, C1 must come before C2. Tracks DFS visitation states, 0 equals unvisited, 1 equals visiting, 2 equals visited. Stores characters in post order for topological sorting. Runs DFS from this character. Returns empty string if a cycle was detected. Builds the final alphabet order. Reverse post order gives a valid topological order. Returns the completed alien alphabet. DFS helper method. A visiting encounter means a cycle exists. Marks character as visiting. DFS into all dependent characters. Marks as fully processed and adds to output list. And that's how the alien dictionary solution works. Build the graph, detect invalid prefix cases, run DFS with cycle checks, and collect characters in reverse post order to form a valid alien alphabet. Now let's quickly verify that this solution works correctly on the given test case. This array is the alien dictionary's sorted word list. It matters because by comparing Z and X, we can infer a direct ordering rule. In the alien alphabet, Z must come before X. Short reasoning of how the algorithm processes the input and what it checks for. The algorithm collects characters, Z, X, initializes adjacency sets, and compares Z with X. At index 0, C1 equals Z and C2 equals differ, so it adds the edge ZX. There is no prefix conflict. Then DFS runs, starting from Z, it visits X, finishing X first, then Z. The post-order list becomes X, Z, which is reversed to ZX as the final order. This output makes sense because it respects the only constraint implied by the input. Z must come before X, so ZX is a valid alien alphabet order consistent with the sorted word list. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's have a quick recap. We're given words sorted in an unknown alphabet, and our job is to reconstruct that alphabet's order. Conceptually, every unique letter is a node in a graph, and the order between letters is inferred by comparing pairs of adjacent words. Wherever the first mismatch occurs, that's a directional edge showing which letter comes before another. The main challenge lies in building the right relationships and detecting cycles. A valid order exists only if the graph has no cycles. We use topological sorting to determine that order, either through Kahn's algorithm, BFS, or DFS. Handling prefix conflicts and missing letters is key to getting it right. Here's the logical plan. Build a graph of all unique letters. Compare every pair of adjacent words to extract edges. Track in degrees for each letter. Run a topological sort, adding zero-indegree nodes to a queue, removing them one by one, and reducing in degrees of their neighbors. If all letters are processed, we have a valid alphabet. If not, there's a cycle, and we return an empty string. We constructed the graph, established edges between characters, and executed Kahn's algorithm cleanly. The program ran successfully on LeetCode without any errors, producing valid alphabet orders for all non-cyclic cases. We verified the solution against various tests, valid dictionaries, invalid prefix cases, and cyclic dependencies, and every scenario behaved exactly as expected. All test cases passed. The key takeaway? Alien Dictionary teaches you how to think in dependencies, how local comparisons build global order. Once you master graph construction and cycle detection, problems that seem alien at first will start to feel like familiar territory.